Okay, let me ask you something. How do you actually know how long a meter is? I mean, really, we all use rulers and measuring tapes, right? But have you ever stopped to think about how we all agreed on what a meter or a centimeter or a kilometer even is? It sounds like such a simple question, but it's got this totally fascinating story behind it. So let's dive in.
So meet Deepa. She's our main character for this story, and her curiosity is going to lead us to a pretty big discovery. It all kicks off with a really simple question she asks her friends. And, it's one of those questions that seems like it has a super obvious answer. But as we'll see, it totally doesn't.
Now, seriously, think about it for a second. If you had absolutely no ruler, no measuring tape, nothing, how would you measure something like a table? And more importantly, how could you and I agree on exactly how long it is? This little puzzle, well, it gets to a massive idea that's at the very heart of all science and engineering. All right, so our story begins in a classroom. We've got Deepa and her friends Anish, Hardeep, Padma, and Tasneem. And they decide to do something that sounds super simple. Measure their classroom table. Easy, right? Well, the tool they picked is where all the trouble started. So they went with a tool that people have been using for like thousands of years. The handspan, or as they call it, a ballista. And the idea is really straightforward. You stretch out your hand and see how many of them it takes to get across something. People have been doing this forever. But it has one huge, glaring flaw, a flaw that these friends were just about to run into head first.
And this is where things get weird. Just look at these results. Anish got a little more than 13 handspans. Padma got exactly 13. Tasneem got a little less than 13. And Hardeep, he got 14. What? How is that even possible? They all measured the same exact table, but their numbers are all over the place.
So that was the puzzle, right? The table obviously didn't change size. So how on earth did they all come up with different answers? It was super confusing, but it pushed them toward a really, really important realization.
And then, ding, the light bulb goes off. Of course. The reason their answers were different is because their hands are all different sizes. It makes perfect sense. Hardeep must have the smallest hands, right? That's why it took 14 of his to get across the table. And Padma's must be a bit bigger, and so on. See, the problem wasn't how they were measuring, it was what they were measuring with. And this really gets to the core of the whole thing. What they were using, the handspan, is called a unit. A unit is just a known amount that you use to measure something unknown. So, using a unit, that was a brilliant idea. But their choice of unit, the handspan, yeah, that was totally unreliable. And you know what? This little classroom experiment shows us the exact problem that people faced all over the world for centuries. If my handspan is different from your handspan, we can never, ever agree on how long something is. Think about it. We couldn't build things together. We couldn't trade stuff fairly. What we needed, what the whole world needed, was a standard. Which brings us to the modern solution, the International System of Units, or what we call SI units. This is it. This is the ultimate answer to the handspan puzzle. It's a set of standards that basically the entire world has agreed on. It took a ton of work and collaboration. But now a meter in Mumbai is the exact same length as a meter in Mexico City. It's like a universal language for measurement. Okay, so we've got these amazing universal standards. Awesome. But, that's only half the battle. Because now you have to know how to actually use them correctly. So let's take a look at the tools and the right way to get these measurements done. So let's start with the big one. Meet the meter. When we're talking about length, the meter is the boss. It's the main SI unit. You can think of it as the world's official, agreed-upon handspan. Every single meter stick, every measuring tape on the planet is based on this one exact length. And that one single standard, the meter, it's the foundation for all the measuring tools we use day to day. You've got the classic meter stick, a flexible tape measure for going around corners and curves, even that little 15-centimeter ruler in your pencil case. They all trace their origins back to that one standard meter. Now, what makes this system so brilliant is how neatly it scales up and down. For really long distances, we just bundle up 1,000 meters and call it a kilometer. For smaller stuff, we chop a meter into 100 little pieces called centimeters, and for super tiny things, we divide one of those centimeters into 10 millimeters. It all just fits together. It's so logical. But remember what Deepa and our friends learned? Just having the right tool isn't enough. You got to use it the right way. I mean, look at this. If you put your ruler down at an angle, like you see on the right, well, you're going to get the wrong answer every single time. So to be accurate, there are basically 3 simple rules to follow. Rule number 1, Make sure your scale is right alongside the thing you're measuring, nice and parallel. Rule 2, look straight down at the reading. If you look at it from the side, the number can look like it's in a different spot. That's a tricky thing called parallax error. And rule 3, if the 0 mark on your ruler is all chipped and broken, no big deal. Just start at the 1 centimeter mark instead, and then remember to subtract that 1 from your final number.
All right, so we've totally nailed how to measure things that are sitting still. But what about things that are moving? Now that opens up a whole new can of worms. It leads to another big question. How do you even know if something is actually moving?
Well, the absolute key to understanding motion is one simple idea: a reference point. A reference point is just a fixed object, a spot that doesn't move that you use to compare things to. You literally cannot say where something is, or even if it's moving, without comparing it to something else.
This milestone here is a perfect example. It says, Delhi 70 kilometers. What does that actually mean? It means your position is 70 kilometers away from the city of Delhi. Delhi is your reference point. But now think about a car driving past. For that car, the milestone itself becomes a reference point to measure its own movement. See how that works?
So, here it is, the big definition. An object is in motion if its position changes over time relative to a reference point. That last part is everything. When you're on a bus and you drive past that milestone, your position, compared to the milestone, is changing. That's motion.
Okay, so now that we've got the basic idea of motion down, let's go on a quick tour of the different kinds of motion. You see these all the time, every single day, and you probably already know exactly what they are. First up, we've got the most straightforward kind, rectilinear motion. Yeah, it's a fancy name, but all it means is moving in a perfectly straight line. You know, like a car on a straight highway, an arrow flying to a target, or these students marching in formation. Simple as that.
Next, we have circular motion. And this one is exactly what it sounds like. Any object moving in a circle. Think about the hands on a clock, the wheels on a bike, or these kids having a blast on the carousel. They're all in circular motion. And what's cool is, even if their speed stays the same, their direction is always changing.
And our last one for today is oscillatory motion. This is any kind of repeating back and forth or to and fro movement. The classic example is a swing set, like this kid is on, but it's also a pendulum in a clock, or even a guitar string when you pluck it, just vibrating back and forth over and over again.
And that brings us to one last kind of mind-bending question for you to think about. Imagine this. You're on a huge ship, and the sea is perfectly glass-smooth calm. You're down below in a cabin with no windows, no portholes. You can't feel any vibration. You can't hear the engine. My question is there any experiment you could do right there inside that room to figure out if you're moving at a steady speed or if you're standing completely still? It's a really tricky one, and it brings everything back to that huge idea of a reference point. Because if you don't have one, how can you ever really know if you're moving at all?